Hello everyone, welcome to this lecture series on thermodynamics. Today in this series, let's discuss Carnot's ideal heat engine, its construction, working and expression for efficiency. The Carnot's heat engine was first proposed by a French engineer, Nicolas Leonard Sadi Carnot, in the year 1824. Of course, he was the first engineer who established the relationship between heat and work. We know that a heat engine is a device which converts the heat energy into mechanical energy. That is, heat energy engines generally transform the thermal energy or heat energy into mechanical energy or work. Of course, they cannot completely transfer the heat energy, input heat energy into work. That is, they cannot do this task perfectly. Some of the input heat energy is converted into work and the remaining is being dissipated as waste heat into the environment. This implies that the engine is not 100% efficient. So we can confirm that no engine will be 100% efficient. We can just improve the efficiency. Hence, for every engine, there is a limit for efficiency. In order to overcome this, or in order to improve the efficiency of a heat engine, for the first time in the year 1824, the French engineer by name Carnot, he devised an ideal engine which is named after his name as Carnot's ideal heat engine or Carnot's heat engine. And the cycle of operation of this heat engine is known as Carnots Cycle. Now let's discuss this Carnot's ideal heat engine under these three subtopics: construction, working and expression for efficiency. First, let's see the construction of a heat engine or construction of Carnot's ideal heat engine. The ideal heat engine consists of the following important parts. The first one is source, sink, working substance and insulating stand. So these four are the important parts of Carnot's ideal heat engine. In the heat engine, we have seen the three parts, important parts: source, sink and working substance. Now in this ideal heat engine, insulating stand is another important part. Now let's discuss the main parts of the Carnot's ideal heat engine individually. First one is source. So here comes the source. Source is a reservoir of heat. Source is a reservoir of heat. It is also known as hot body. This is always maintained at a constant high temperature T1. Its thermal capacity is very, very high. That means even though some amount of heat is drawn from the source, its temperature will remain the same. It will not change. It is always maintained at constant high temperature T1. Here, the two sides and the bottom portion are made up of adiabatic walls. Only the upper portion is conducting. That is, the two side walls and the lower portion are non-conducting walls, are made up of non-conducting walls, and only the upper portion is conducting. This is regarding the source. Next important part of heat engine or ideal heat engine is sink. Here comes the sink. Sink is also a reservoir of heat. Like source, sink is also a reservoir of heat. Sink is maintained at constant low temperature T2. Here source is maintained at constant high temperature T1, whereas sink is maintained at low temperature T2. Its thermal capacity is also very, very high. That means even though certain amount of heat is taken away or some amount of heat is added to this sink, the temperature will not change. It always remains constant at T2. Here also you can see that the two side walls and the lower portion are made up of non-conducting walls and only the upper portion is conducting. The sink is also known as the cold body. This is known as hot body. This is known as the cold body. So this is regarding the sink. The thermal capacity of source and sink are very, very high. Next comes the third important part of Carnot's ideal heat engine, which is known as working substance, Generally, ideal gas is taken as the working substance. It is generally taken in a cylindrical vessel which is fitted with a frictionless non-conducting piston. The two sides of this cylindrical vessel are made up of non-conducting walls. Lower portion, that is the bottom portion, is conducting. So what is the working substance? Ideal gas taken in a cylindrical vessel constitutes the working substance. The last and important part of the Carnot's ideal heat engine is insulating stand. This is made up of perfectly non-conducting walls or perfectly non-conducting platform. This is useful to perform adiabatic operations, that is adiabatic expansion and adiabatic compression. So these four are the main parts of Carnot's ideal heat engine: source, sink, working substance, and insulating stand. Now let's see the working of Carnot's ideal heat engine. The working of Carnot's heat engine can be well understood with the help of a cycle which is known as Carnots cycle. So under the working, we can see the Carnot's engine has four stages of operation. The first one is isothermal expansion. Second one is adiabatic expansion. The third one is isothermal compression. And fourth one is adiabatic compression. So this is the complete cycle: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. This cycle is known as Carnot cycle. Now let's try to understand the working of Carnot's heat engine by considering the four stages of operation individually. Now let's see the first stage of operation, that is isothermal expansion. So here, generally, the isothermal expansion can be understood with the help of the Carnot cycle, or we call this as PV diagram. In a PV diagram, volume is taken on x-axis and pressure is taken on the y-axis. Now let's consider 1 mole of an ideal gas which is enclosed in the cylindrical vessel. But let's consider 1 mole of ideal gas which is taken in the cylindrical vessel which is fitted with a frictionless piston. Let the initial state of the gas be represented by the point A, whose pressure is P1 and volume is V1 and temperature is T1. That is, P1, V1 and T1 represent the initial state of the gas which is taken in the cylindrical vessel. V1 represents its volume, P1 represents its pressure. This is the initial state of the gas. Now, this cylindrical vessel, that is the working substance, is then taken and it is placed on the source. You can see the upper portion of the source is conducting, lower portion of the working substance is also conducting. This working substance is placed on the source. The source has the capacity to supply the heat. The working substance has the capacity to absorb the heat. So the source supplies the heat and this working substance absorbs the heat. Now, when this piston is allowed to move slowly outwards such that the gas expands, the volume changes from V1 to V2, the pressure changes from P1 to P2. This is represented by the point B. This is the initial state. This is the final state. This is the expansion process represented by AB. Since it is carried at constant temperature T1, we call it as isothermal expansion process. So AB on the indicator diagram indicates the isothermal expansion process. Now let us assume that Q1 is the quantity of heat absorbed by the ideal gas in the process of expansion. When it absorbs certain amount of heat, an equivalent amount of work is done. So let W1 represents the corresponding amount of work done. Q1 is the quantity of heat absorbed and corresponding work done is W. This is according to first law of thermodynamics. So Q1 is equal to W1. So when Q1 amount of heat is given, then an equivalent amount of work is done, which is equal to W and W1, and is equal to RT1 log V2 by V1. This we have derived in the work done in isothermal expansion process. So T1 represents the initial temperature, V1 and V2 represents the initial and final volumes, or is the universal gas constant. So work done in the isothermal process is given by the expression W1 is equal to RT1 log V2 by V1. So this is the first stage of operation, and we have calculated the work done in the first stage of operation. Similarly, let's see what happens in the second stage of operation, that is adiabatic expansion process. So next comes the adiabatic expansion process. Here B is the initial state. B becomes the initial state. Previously for this operation it was the final state. The final state becomes the initial state now. V2 and P2 represents the initial volume and pressure of this gas. Now the working substance which was previously on the source, it is removed and it is placed on the insulating stand. We know that insulating stand is must to perform the adiabatic operations. Since we are carrying the adiabatic expansion process, the working substance which was previously on the source, it is removed from the source and it is placed on the stand. Now the piston is slowly moved outwards, then the gas gets expanded and the volume changes from V2 to V3 and pressure changes from P2 to P3. The temperature T1 falls to T2. The temperature T1 falls to T2. So now the C is the final state of the gas whose coordinates are V3 and P3. So the gas has undergone an operation which is known as adiabatic expansion process, and it is represented on the indicator diagram by the curve B.Sc. So B.Sc represents the adiabatic expansion process. So when the gas is undergoing expansion, naturally it does certain amount of work. Let W2 be the work done by the gas in the process of expansion of adiabatic expansion. So W2 can be written as R by gamma minus 1 into T1 minus T2, where T1 and T2 represent the initial and final temperatures. So this is the work done, expression for the work done in the process of adiabatic expansion. And this is the second stage of operation. First stage is isothermal expansion. Second stage is adiabatic expansion. Now let's see the next stage of operation. First, we have allowed the gas to expand isothermally, allowed the gas to expand adiabatically. Now, in order to reach its initial state, it should undergo the reversible process. That is, it should undergo isothermal compression and also adiabatic compression. Now, let's see the next stage of operation, that is the third stage, which is known as isothermal compression process. So, here comes the isothermal compression process. Now, here the CV3P3 will become the initial state. Now, the working substance which was previously on the insulating stand is removed from the insulating stand and it is placed on the sink. When it is placed on the sink, here you can see the lower portion is conducting, the upper portion is conducting. We have already studied that sink has the capacity of absorbing the heat. Now the working substance is placed on the sink. The piston is slowly moved downwards in order to compress the gas isothermally. When it is compressed, then what happens? The temperature of the gas remains constant at T2. The volume and pressure changes to V4 and P4. Volume and pressure changes to V4 and P4. This is represented on the indicator diagram by D, V4, P4. So CD represents the isothermal compression process. CD represents the isothermal compression process. So here Q2, let Q2 be the amount of heat rejected. Q2 be the amount of heat rejected. In this process, it has absorbed a quantity of heat Q1. In order to attain this state, it should liberate or reject the same amount of heat. So Q2 be the amount of heat rejected to the sink and corresponding amount of work be W3. Q2 is the quantity of heat rejected and W3 is the amount of work done. So Q2 is equal to W3, which is equal to RT2 log V4 by V3. So this is the expression for the work done in isothermal compression process, which is represented by CD on the indicator diagram. Now let's see the last stage of operation, that is adiabatic compression process. So here comes the adiabatic compression process. So here D becomes the initial state, V4 and P4. Now the working substance which was on the sink is taken away from the sink and it is placed on the insulating stand in order to perform the adiabatic compression. When it is placed on the stand and the piston is slowly moved inwards, then the gas gets compressed. Since it is on the insulating stand, this process is taking place adiabatically. We call it as adiabatic compression process, and the gas gets compressed to V1 and the P1. That is, the volume gets compressed to V1 and pressure changes to P1. So dA represents the adiabatic compression process. dA represents the adiabatic compression process. So in the process of compression, let W4 be the work done on the gas in compressing it adiabatically from a stage D to A. So dA represents the adiabatic compression process. And now let's see the work done in this process. W4 represents the work done in adiabatic compression process given by the expression R by gamma minus 1 into T2 minus T1. So this is the work done in the adiabatic compression process. So till now we have studied all the 4 stages of operation: isothermal expansion, adiabatic expansion, isothermal compression and adiabatic compression. Now in order to calculate the work done, this is W1, W2, W3 and W4. If we put all the amount of work done in the 4 stages, we will get the total work done in the process. Now let's calculate the total work done by the heat engine by making use of this Carnot cycle. So total work done in the cycle. W is equal to W1 plus W2 plus W3 plus W4. Putting all the expressions together, we can write it like this. Or see here, plus R by gamma minus 1 into T2 minus T1, or we can write it as minus R by gamma minus 1 into T1 minus T2. So these two gets cancelled. We will get W is equal to RT1 log V2 by V1 plus RT2 log V4 by V3. So this is the work done in isothermal process, which is equal to W1. This is then work done in isothermal compression process, W3, expansion process and compression process. So the total work done by the Carnot's heat engine will be ultimately W is equal to W1 plus W3. So this is the total work done in the Carnots cycle. Now let's understand or let's calculate the expression for the efficiency of ideal heat engine. We know that efficiency is defined as the ratio of work done to the quantity of heat absorbed and is denoted by eta. Eta is equal to W by Q1. W is the quantity of work done and Q1 is the amount of heat absorbed. W by Q1. So this is the expression for W which we got in the previous slide, and this is the expression for Q1. Q1 is nothing but W1. So this is W1 plus W3 by W1. Now, in order to simplify this equation, let's see, we know that here you can see this is the adiabatic expansion process. B.Sc represents the adiabatic expansion process. These 2 points B and C lie on the same adiabatic curve B.Sc. Now, we know that all the adiabatic changes are represented by the equation TV to the power of gamma minus 1 is equal to constant. Now, making use of this relation, we can simplify and write it like this. T1 V2 to the power of gamma minus 1. T1 V2 to the power of gamma minus 1 is equal to T2 V3 to the power of gamma minus 1. Here the temperature is T1. Here the temperature has fallen to T2. So T1 V2 to the power of gamma minus 1 is equal to T2 V3 to the power of gamma minus 1. Or T1 by T2 is equal to V3 to the power of gamma minus 1 by V2 to the power of gamma minus 1. Similarly, these 2 points, dA represents another adiabatic compression process. D and A lie on the same adiabatic curve. Making use of the same equation and simplifying, we will get this equation. Now, simplifying these two equations, 2 and 3, we will finally arrive at V2 by V1 is equal to V3 by V4. Substituting this equation in equation 1, we will get eta is equal to T1 minus T2 by T1 or 1 minus T2 by T1, which is an important expression for efficiency. Eta is equal to 1 minus T2 by T1. From this expression, it is clear that the efficiency of an ideal heat engine depends only on the initial and final temperatures, but it does not depend upon the nature of the working substance. So this is the expression for efficiency. Now, let's see some of the applications of Carnot's heat engine. So, all types of vehicles that we use in our daily life, cars, motorcycles, trucks, ships, aeroplanes, and many other types work on the basis of second law of thermodynamics and Carnots cycle. Of course, they can use either petrol engine or diesel engine, but the law remains the same. All the refrigerators, deep freezers, industrial refrigeration systems, and all types of air conditioning systems, heat pumps, all work on the basis of Carnot cycle. Hope you have understood the Carnot's ideal heat engine, its construction, working, and also the expression for efficiency. Thank you.